For the experiments, to construct the heterogeneous graph, a large molecular drug and patient dataset was used. In particular, protein-protein interactions that are physically documented in humans, drug-target relationships, and side effects of drug pairs from a resource developed at Columbia University were also used. So altogether, that resulted in a heterogeneous multimodal graph that we have seen before with around 1000 types of edges. After constructing this graph, a prediction task was formed as follows. In the training phase, we fit a model on known side effects of drug pairs. In the testing phase, given a query drug pair, all types of side effects associated with that query drug pair were predicted. There are a number of different settings that were considered to prevent any circularity in the data. The performance here is measured in terms of two metrics. In particular, area under C-curve and average precision was at 50, where the top 50 predictions were looked at and the accuracy for those was considered. Decagon, shown in red, was compared with a few other alternatives. What can be learned from this is that it performs much better than tensor-based factorization models. The reason why this is the case is because we are using graph convolutional encoder. It performs much better than two-stage pipelines where you take a network first, extract features, take the feature vectors, and train a downstream classifier. And this is because we have an end-to-end pipeline and an end-to-end model. Just to conclude, the team of researchers was also interested in doing de novo predictions. In particular, associations between all possible drug pairs and side effects were predicted and ranked by their predicted probability score. The top 10 predictions that were not in the data can be seen, and biological evidence was looked for to back the predictions up. It turns out that about 5 out of the 10 predictions could be supported by evidence, and the other predictions are currently being explored at Stanford by the Spark Translational Research Center. So to conclude today, we talked about Decagon, which is a graph neural network that can work up and operate on heterogeneous graphs. It offers lots of flexibility and is super scalable. It can integrate site information in terms of node features on the nodes, which wasn't described in this presentation. This is the first method that you can predict drug and model drug combinations. It can be useful to predict drug combinations not yet used in patients. The code and data for this project is rolled up at snap.stanford.edu/decagon, and all the materials about deep learning for natural biology can be accessed at the other website. Thank you.